is Ednei Aparecido Santulo Jr. He is at the University of Maringá in Paraná, Brazil, and his talk is group gradings on incidence algebras. I'm not going to present him mathematically. I simply want to say that his advisor, Koshlukov, was my student, so he is my grandchild from scientific point of view. And of course, Yuri Bakhturin here, he is his grandfather. And since his student Johnson is here, we are 5 generations. Okay, Plamin, I'm not sure Plamin is here, but we are 5 generations of mathematicians of algebras. So, okay, Ednei, you can start.
Sorry, I had a problem here. Can you see me? I just realized. Just a minute, please.
Okay,
Yes,
we can see that you.
And we can see your slide.
We can see that we can. Okay,
yeah,
now we see you.
No, because the battery of the laptop is low and I had to plug it.
Okay, now we see you.
Okay, I'd like to thank you for the invitation to give this talk about my work with Felipe Yasumura and Jonathan Souza. I will talk about group gradings on incidence algebras, and I'd like to start by apologizing because I was worried when I was planning this talk. There could be many postgrad, doctorate and master students, so I tried to maybe it will sound like elementary, some things but I wanted to be sure that everyone who would be attending the talk would understand the general setting of the problem and the objects we deal with. Okay, so let's start. Minute. Yeah. So I start by defining incidence algebras. So for us, X will be always a finite partly ordered set. By short, we just say set for that. Okay. There's a mistake here in writing. It's not a file, it's a field. A is a field. And we define the incidence algebra of X over K as the set of maps from X times X to K, such that the image of the pair XY is 0 whenever X is not less than or equal to Y. Okay? When X is finite, I am imposing X finite, but this is not necessary at all. You can have more general settings for incidence algebras to define an incidence algebra. But in this case, we can label the elements of X in such a way that it happens when Xi is less than or equals to Xj, then I is less than or equals to J in the natural numbers. And this is very useful because in this case, this map, which maps each F to the matrix where the ij entry equals to the image of the pair xi xj, this allows us to see the incidence algebra as a subalgebra of the triangular upper triangular matrix algebra. Okay. They were introduced by Giancarlo Rota in 1964 with combinatorial motivation, studying Möbius function. And as I said before, we can always see them like as subalgebra of UTN when X is finite. But in more general settings, they were well-behaved generalizations for UTN. And even the finite case may be much trickier than UTN, which is the case here of group grading algebras in incidence algebras. Okay. When X is a chain, this means that every element of X is comparable with any other element of X. We have this isomorphism between the incidence algebra and the algebra of upper triangular matrices. And let's start talking about group gradings on K algebras, and then I will look from here the group gradings on instance algebra. So G is a group, K is a field, A K algebra. So a degrading on A is a decomposition in the direct sum of the linear space of subspaces indexed by the element of G. And we must have this equality here. Can you see my point mouse or not?
Yes, we can.
Okay. And we have this condition here. So by short, we have these two things happening. And algebras of polynomials are naturally graded by the degree of the polynomial. Group gradings were important for the classification of finite dimensional semi-simple Lie algebras, and an example from one of the areas I worked is they were very important in Cambridge solution of expressed conjecture on PI theory about the finite if every T ideal of polynomial identity is finitely generated. So we can define some equivalence relations between gradings in an algebra. So two different G gradings in an algebra A, we say they are isomorphic if there exists an automorphism of A. Here we have one grading, here we have another grading, such that each component for the first, for the same G, for the first grading is mapped into the same components between quotes, because indexed by the same G in this other grading here. This is called a graded isomorphism or automorphism in this case. Right? So when we have two different degradings on A, we say that they are equivalent if there exists an automorphism of G now. So this is different. There we had an automorphism of A, and now we have an automorphism of G, such that the component AG in the first grading is mapped to is the component A psi G in the second grading. Okay, so we changed the indices. So we want to classify for a fixed group G all the G gradings on the incidence algebra up to isomorphism, right? We have worked with equivalence too in the paper, but I won't talk about that here because I thought it would be very long, but now I'm worried that it will be very short. I don't know if I have planned very well the time. So history of grading classification on UTN, this was partially made by Vincenzo, Koshlukov and Valenti in 2004, when they also study graded polynomial identities for UTN, and they proved that every degrading on UTN is isomorphic to an elementary grading. But what is an elementary grading? So if you denote by EIJ the matrix n by n, such that the ij entry equals 1 and all the other entries are zeros. And this is usually called unit matrices in some works. I particularly don't like that name because it sounds like these matrices can have inverse, but I don't know a better name for them. So this is the standard basis of matrices. We say that the degrading on MEN is the full matrix algebra, or any subalgebra of MEN expanded by a subset of the standard basis, which is the case of UTN and of incidence algebras when we see them as subalgebras of UTN. So we say that the degrading is good if every EIJ is D-homogeneous. This means that every EIJ is in subspace which appears in the decomposition of A. Okay, and we say that degrading is elementary if, moreover, it must be good and there must exist a map F from the set of indices G such that the degree, this is the index of the component where this would be that G here. This is given by this relation involving F. Yeah. So in MN and UTN, everybody degrading also is elementary, but this is not always the case in instance algebras. For instance, if we consider this pole set here, so this is the half diagram of the pole set. This means that 1 is less than 3 and less than 4, 2 is less than 3 and less than 4, but 3 and 4 are not comparable one with each other, and the same for 1 and 2. So you can see the instance algebra as this algebra of matrices. Okay. If you have a non-trivial group G and you pick a little g in here, and you can consider the component AG as expanded by E14 and the trivial component expanded by all other matrices, EIJ. So this is good because the standard basis is homogeneous, but this is not elementary because since the degree of E14 is different from the unit of the group, you must have different images for 1 and 4 through F, but it cannot happen because E13, E23, and E24 have all trivial degrees. So this can't be done. Classical example. So it's good, but it's not elementary. When D is abelian, one can turn the set of all good degradings of IX into an abelian group in a very natural way. You just multiply by multiplying the indices of the components. And it turns out that the subset of all elementary gradings of IX is a subgroup of that group, and since this is an abelian group, obviously this is a normal subgroup, so you can make a quotient here. And in the case of incidence algebras, this is isomorphic to the first cohomology group of the poset X with coefficients in the group G. And this is a particular case of a more general result obtained by Laet Ben, Erika Fornaroli, and myself in 2019. So I will talk about a little here about this more general setting because it will appear later in my talk. So when you have B, a multiplicative base of your key algebra A, and this means that when we have any two elements of this base and multiply them, the result is 0 or a scalar multiple of another element of the basis. So I say that degrading is B good if every element of B is G homogeneous. And if there exists a subset I of B of pairwise orthogonal idempotents, such that for all B in B, you can find UB and VB in I, satisfying this condition here. And there exists a map F from I to G, satisfying that condition. So the trick here is changing the set of indices 1 to n for the idempotents, because the indices are uniquely related to an idempotent, a primitive idempotent of Mn. You correspond I to EII, to the matrix EII. So this was the way we found to generalize the concepts of good gradings and elementary gradings. And here you have some good things because you can generalize the concept for a wider class of algebras, and we have a similar result to this one in this class of algebras. On the other hand, it may happen that the same algebra can have two different bases satisfying that condition, being multiplicative with this condition here. And there will be gradients which are elementary for one gradient, for one basis, for B elementary for one B, basis B, but not C elementary for another different basis which satisfies the same condition here. So it's maybe interesting. But let's go back to our problem. It's not even true that average grading on IX is isomorphic to a good grading. So if you consider this poset here, and we have this algebra, the incidence algebra is isomorphic to this, and this is C2 times C2, the C group of order 2. I prefer the multiplicative notation for it in this context. And you consider this grading here. This is not this is not isomorphic to a good degrading, because to be isomorphic to a good degrading, the dimension of the trivial component would be at least 3. And here the trivial component has dimension 2. So it is not isomorphic to a good degrading for sure. Although there is a homogeneous multiplicative basis here. So this is not good in the usual sense, but it's good in the be good with respect to a multiplicative basis be homogeneous. So in this example, we can split the algebra in a component isomorphic to the field. Here we have this component, which is a C2 graded division algebra. I will talk with grade division algebra soon. And here we have a KD by module, a graded KD by module. But what is a graded division algebra? It's a degraded algebra where every non-zero homogeneous element has inverse. Okay? So it's a unit. And M is a C2 graded KD by module. So this denotes the order of the block. This is a block 2 by 2. This is a block 2 by 1, and here you have a block 1 by 1. So every degrading on IX is isomorphic to a degrading where you have blocks on diagonal of this form, and each block is a graded division algebra, and each MID is a grade DI DJ by module. Okay, so now I will present how to get here. So here are the main steps to obtain the previous result. We consider this the set of homogeneous idempotents of IX with respect to grading. And then we consider a pre-order. This is not a partial order in general, but it's a pre-order where you an idempotent is less than another one if you have this continuous here. So since we are dealing with finite pole sets, the dimension of the instance algebra is finite, and we can guarantee that there are minimal elements here. This is not empty because the identity is always here, right? So there will really be some minimal elements. Now we need a lemma. If E1, blah, 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 ER are orthogonal idempotents in an incidence algebra, we can simultaneously diagonalize all of them. Okay, so it's the same that saying there's an inner automorphism for which they are all diagonal. So this grading is isomorphic to one with minimal diagonal element in that set. So we can assume there's a diagonal and minimal element idempotent in that way. And we fixed such a minimal element. And we denote by B this subalgebra of IX. And we see that if you take a non-zero element of B, which is not in the Jacobson radical of E, and this is the intersection of the Jacobson radical of the algebra with B, we can find an M natural such that this cannot be true. Here it's necessary. The degree of X is homogeneous, right? So this must be homogeneous. So the G degree of x to n is trivial. Okay, I'm sorry, here's my mistake. And it happens because since x is homogeneous, every power of x is homogeneous, and since the dimension is finite, it cannot happen that you have an infinite linear independent subset, and there will be repetitions of degrees, and with this we obtain that for some power it will be in the trivial component of the grading. We need that the Jacobson radical is D-homogeneous. This is a result by Gordienko when the characteristic of the field is 0 or more than the dimension of the algebra. But this is also the case when we're dealing with a commutative, an abelian group in the grading, because when you apply because the Jacobson radical of the incidence algebra is the commutator of the algebra with itself, and if you have the G abelian, UV and VU have the same degree if they are homogeneous elements, and this assure us that the Jacobson radical is homogeneous. So these two cases do the result by Gordienko, and this is analyzed in this best way. Thus, this quotient here is degraded. So we decompose it into a direct sum of homogeneous components, and we claim that dimension of the trivial component is 1. This is achieved due to the minimality of E. I won't make details here, but the question, if this dimension is not 1, you would find another idempotent element who's less than E and not equals to E, so it wouldn't be minimal. If you have a G homogeneous element in this quotient, non-zero, again, we can find a natural and satisfying this condition. Now this is correct because this dimension is 1. No, yes. And this implies that the quotient is a great division algebra. And since this dimension is 1, the dimension of all components is 1, 2. Okay. Here, there are some tricky arguments I'm hiding. So let I be the least positive integer such that the II entry of E is different from 0. Then when you multiply the Jacobson radical, factor of Jacobson radical over the square of the radical by EII, we got 0 here because it can't. The Jacobson radical is formed by is spanned by the EIJs with I strictly less than J. You don't have the diagonal part. So since this is the least positive integer, this trivially is 0. But this is not 0 in the quotient. So the annihilator of this, the right annihilator of this here is not 0, but it must be a homogeneous subspace of B over JB, which is a graded division algebra. So you would have a non-zero homogeneous element which would annihilate this, but it is inversible, so it cannot happen unless this is 0. But if this is 0, it means the Jacobson radical is 0, and B is a graded division algebra. So since the beginning, this was isomorphic to B. And since this is a graded division algebra, B is a graded division algebra. Okay? So a corollary, if ij in X satisfy this condition, the entries ii and jj of E are different from 0, then I cannot be comparable with J, because otherwise we would have a non-zero Jacobson radical, or B. So each component is one-dimensional, and where each f has finite order because of the finite dimension. So we consider the order of such elements will coincide with the order of this index in the group. And inductively, we found a minimal or idempotent and diagonal idempotent. Then we consider pi plus 1 this set of homogeneous idempotents. Homogeneous, I forgot here. And we construct E1, E2, E3, and we can require all them to be orthogonal because since they are orthogonal, if they are not diagonal, no, we can require they are orthogonal. This is wrong. We can require them to be diagonal, sorry. And this is due to they are orthogonal and they commute, so they are simultaneously diagonalizable for the previous result I presented here. And the block di, we can consider EI, IX, EI, so you're almost getting the result. But we must check that you can dispose them in the diagonal of the matrix in that way, not splitting the I over the diagonal. So this will be a commutative diagonal graded division subalgebra of IX. Now we define, this is a partial order on that orthogonal idempotents. So this happens if this is different from 0. This is a partial order. So you can rearrange the EIs in such a way that this implies this. Again, this is quite similar to the claim I did in the start of the presentation. And if EI is less than EJ, and this happens, K is comparable to L, then and K is comparable to L, then K is less than L. This is important for then because we can now dispose the DIs over the diagonal in that way. This means it cannot happen that we have a part of D1 here, then a part of D2 here, and after another part of D1 here. So we can really order the blocks over the diagonal in this way. And here, these MIDs will be just these DI, DJ by modules here. And they will be also degraded. Okay? The main results of the paper are necessary conditions for 2 gradings. So we have this, and then, okay, every G grading has this form. It's isomorphic to a grading of this form. But when we have two gradings of this form, how can we know if they are isomorphic or not? So in the paper, we present some necessary conditions for two gradings of that type to be isomorphic, and a complete classification for the case when G is a billion. Okay. So let's return to our motivating example. This was A. You had, these are 3 by 3, and you had a minimal element with two maximal elements here, and we split the algebra in such a way. So as I commented before, this is not a good grading in the usual sense, but it's good in the generalized sense because you have a multiplicative basis, which is homogeneous with respect to its grading. So we can wonder if this is always the case. But happily, this is not true. So here's a counter example, which is not very simple. You consider this partially ordered set here. You have minimal elements 1 and 2. Then you have 3, 4, 5, and 6 connect with 1 and 2 in this way, and 7 and 8 maximal elements. And we consider this Z2 times Z grading on IX with all those relations here and more those relations here. And this is not, you cannot find a homogeneous multiplicative basis with respect to this grading. So this is not a good grading, not even in the generalized sense. Thank you very much. Merci.
Okay. We thank you very much. Do you have any comments or questions? You can simply ask, no need to raise hand or something.
I guess I have a question.
Okay.
Yeah.
If you start with a partially ordered set, the corresponding algebra is a subalgebra of the upper triangular matrices.
Mm-hmm.
What about weakening the condition so you only have a set with a transitive relation, such as I have studied? Is there any hope of generalizing it in this direction?
I have not dealt with this context barely, but I'm afraid not, because even here, in this case, when make very few changes in the partially ordered set, we have many changes, but it may happen. But if I have to guess, I would say I don't think so, but I didn't try to make calculations in the same.
Some other questions or comments? If no, yes, thank the speaker once again for the nice talk. Okay,
thank you very much.
Make this one.
I apologize because as I said in the beginning, I was expecting more students to attend the talk than professional mathematicians. I think I should have prepared a more.
No, it's also okay because we had Department of Algebra and Logic. So there are people doing different parts of algebra, different parts of logic. So I think every talk has to have a part which is general to be understood by all the people, and some part which should be for elected persons doing in the topic, doing work in this, so it's okay. I like the talk very much. By the way, I want to make some announcements about the next talks. The next talk, the next Friday, it will be by 4 speakers. Ilinka Dimitrova, she is from the Southwestern University in Bulgaria, not in the States. And this is a joint talk with a German who works from our institute, and your Kopitz, and 2 persons from the, I think from the Philippines. Then there will be a talk by Michael Vaughan on finite groups. He's from Oxford. Then the next Friday there will be a talk by a colleague of us, Yubomir Borisov. He's doing something in the midpoint of algebra and number theory. Then there is a talk by Bogdana Olejnik. She is from Kiev. The talk will be announced on the homepage of the seminar. Then there is a talk by Arkady Srinko. He is originally from Russia, but now he's in New Zealand. And that his talk will be early in the morning for us because there are 9 hours difference in the time. But it will be, you know that Srinko, Zhivakov, Shestakov, and Shirshov, they have the Bible on Jordan algebras, and rings which are nearly associative or close to associative. I don't remember the English translation of the title. But his talk will be on cryptography. Also, there is a talk by Virginia Vasilevska-Williams. She will give something about fast multiplication of matrices. She gave a talk in the International Congress in one of the sections on mathematical aspects of computer science. And by Greta Panova, she is from LA. She is also Bulgarian, about something concerning tensor products of symmetry groups, presentations representation of the symmetry group. I also make 2 more announcements. On the 31st of May, this is Monday, in Hungary, there will be a talk on quantum computing or something of this kind. You can, you know that we have an agreement with the seminar in the Reni Institute of Mathematics in Budapest, so we'll be informed about this. And also the 1st of June at 2 p.m. Bulgarian time, this is 11 in the morning Greenwich Mean Time, there will be a talk on coding theory, but this talk is organized by our section, our Department of Mathematical Foundations of Informatics, jointly with Novosibirsk, and it will be something about coding theory. So you can see this information from the homepage of our seminar, of course, and also the seminar in Budapest. And in the homepage of our institute, usually we announce the seminars. So if you're interested in this seminar on coding theory, you can ask me or you can simply visit the homepage. I can give you some information. So you can stop recording, I think, or you already stopped.
I will stop